In the deep quiet of space, a clock can be made from pure motion. Pulsars spin with astonishing regularity, sending beams that sweep like steady lighthouse arcs through darkness. Tonight's journey follows those pulses, traces how a neutron star can rival atomic clocks and how tiny delays reveal hidden structure across the cosmos. If this kind of calm science storytelling helps, please tap like and subscribe for more long-form sleep documentaries. Set the bell for new episodes and sink into the rhythm of time itself. A pulse arrives as a repeated shape in deep space separated by an interval that barely drifts. The steady spacing comes from rotation that changes with extreme slowness. In that region, a neutron star turns with a smoothness that ordinary matter rarely maintains. A compact object spins and a narrow beam sweeps across a distant direction. Each sweep becomes a tick. The scene settles on a small sphere that holds enormous mass in a tiny volume. The surface is dark except for faint ovals near a tilted magnetic pole. A thin sheath of charged particles clings above those ovals and glows softly. The magnetic pole sits away from the spin axis, so the beam traces a circle through space. Far beyond the star, a pale filament of gas hangs like a suspended thread. When the beam crosses that filament, the filament brightens for an instant. Then darkness returns. After the same calm pause, the brief glow arrives again. The pattern holds. The first concept is rotational stability. Rotation becomes a clock when the spin rate changes predictably and slowly. A neutron star is compact and it offers little leverage for braking. Its spin therefore keeps a clean rhythm over long spans. Many pulsars turn in about 1 second. Some turn in a few thousandths of a second. The contrast resembles slow drops and fine drips from the same cold ceiling. A repeated interval can mark time because the next interval resembles the last. A second visual anchor appears inside the pulse profile itself. The pulse is not a point. It has a leading edge that rises quickly. It has a trailing edge that fades more slowly. The edges come from geometry rather than chance. The beam has a bright core and a softer skirt. As the star rotates, the core crosses first. Then the skirt follows. The same sequence returns on the next rotation and the timing mark sharpens. The main number does not need to be huge. It only needs to be steady. About 1 second between ticks is enough to build a long timeline. Over a day, the interval repeats many tens of thousands of times. Over a year, the repetition becomes so large that tiny drifts stand out. The comparison is like waves arriving on a quiet shore. One wave reaches the sand, another follows. The spacing stays almost unchanged. Stability across vast counts turns a distant object into a reference rather than a surprise. The second concept is rigidity under extreme gravity. A neutron star is matter pressed into a tight sphere, and its outer crust is solid and strongly bound. A wobble cannot easily grow and wander across the surface. That reduces precession. Precession is a slow change in the spin direction. A winged seed can spin while drifting downward and its axis can slowly sweep a circle. In a neutron star, stiffness and gravity suppress that slow sweep. The surface curvature is sharp and the gravitational gradient is steep. Those conditions help lock the rotation into stable balance. Less wobble means less timing smear, so the tick stays narrow in time. The view shifts outward across the long path between the star and far distance. The beam leaves the magnetized region and travels through interstellar space. That space contains a thin fog of free electrons. The fog delays some parts of the signal more than others. Dispersion is a frequency-dependent delay in signal arrival. Lower frequencies lag and higher frequencies arrive earlier. The same pulse can stretch and a sharp front can soften into a longer tail. The visual becomes a crossing through layered mist. A bright ripple enters crisp but then exits with a softened edge. The repeated pulse makes that stretching predictable so the underlying cadence stays recoverable. A limit of observation enters without drama. The star is too small and too distant to appear as a resolved disk. Only the changing beam appears as a pattern in time at a far point in space. The beam is not perfectly constant. The plasma above the pole can shift and that can add small jitter to the pulse shape. The electron fog along the path can change slowly, and that can add slow wander to arrival times. A single pulse cannot establish a clock. Only long accumulation reveals the cadence beneath short fluctuations. The limit is specific. Timing depends on indirect inference from arrival times, not on direct inspection of the rotating surface. Averaging many ticks lets the stable interval emerge from small irregularities. It resembles an undertow beneath surface ripples. The analogy for the section stays natural and singular. The pulse train resembles drops forming on a stalactite in a silent cave. Each drop swells at a narrow tip, then separates and falls. Each impact sends a ring that expands across still water, then fades. The rhythm persists in silence, and the spacing remains consistent. A pulsar behaves in the same spirit on a larger scale. The beam forms, it sweeps, it returns. The tick is not heard yet. It is written as repeating spacing carried through darkness. Scale shifts soften the edges of intuition. The emitting region above the pole can be small compared with the star. The star itself can be smaller than a city in diameter, yet the signal can cross like years before it weakens into background. A tick can last 1,000th of a second, yet the pattern can persist across years. In that region, an object would carry rotation forward as a kind of memory. The memory is a sequence of intervals that remain consistent, and that consistency can rival clocks based on atomic transitions. The closing image returns to the tilted pole and its faint ovals. As rotation continues, the ovals brighten and dim in regular cadence. The beam sweeps out into the cold medium. The distant gas filament brightens briefly again. Then it dims again, with the same calm pause between events. If the pulse can be predicted far ahead, then any tiny deviation can reveal a cause with minimal confusion. The next section moves from the tick itself toward the compact physics that shapes the beam and protects its steadiness. The clock-like pulse begins long before it becomes a beam in the quiet geometry of a collapsed core. The steadiness is protected by a star-sized mass packed into a sphere about 20 kilometers across, like a small city folded into a single smooth pebble. In that region, gravity grips so strongly that the surface curvature feels abrupt. The crust sits as a thin, solid skin. Beneath it, matter presses into layers that resist easy deformation. The visible clue is not colour or shape in an image. It is the refusal of the rotation to wander. A dark sphere turns, and the turning stays centred. A faint oval of emission clings to a polar cap. The cap has a sharp boundary. The boundary is a rim where field lines open outward. The rim traces a ring-like edge that stays fixed on the surface as the star spins. That stable rim becomes a stable reference. The first concept is conservation of angular momentum. Angular momentum is spin that resists change without outside torque. When a massive core collapses, the radius shrinks, the spin speeds up and the new spin can remain. A familiar analogy keeps it gentle. A figure skater pulls arms inward and turns faster. In space, the collapse performs a similar inward pull without intention. The payoff is immediate. The fast rotation is not a special trick. It is the natural outcome of shrinking size. The next visual anchor stays close to the surface. The polar region is not flat. It is a curved cap where magnetic field lines emerge and return. Some lines close back to the surface, others extend outward into space. The open lines create a funnel. Charged particles slide along that funnel and form a thin, accelerating layer above the cap. A narrow beam follows the open lines. The beam is narrow because the open region is narrow. The cap is small compared with the whole star. That geometry makes the tick sharp. A sharp tick is easier to time. The second concept is magnetosphere structure. A magnetosphere is the region where magnetic fields guide charged particles. In a pulsar, the field is strong and organized near the surface. It forces motion into narrow channels. The channels create a beam with a bright core and a softer skirt. The core produces a steep pulse edge. The skirt produces a slower fade. The payoff arrives again. The pulse profile repeats because the channels repeat. The star rotates and the same channel sweeps past the same far direction. The shape stays similar because the field geometry changes slowly. A new visual anchor drifts outward along the field. The open lines widen as distance increases. The beam also widens, yet it stays coherent. It stays aligned with the rotating structure. The beam crosses a region of sparse gas. The gas is so thin that it looks like a faint haze. Light behaves as a clean stream through that haze. Scattering is present but small. The pulse arrives as a crisp marker. The clock-like behaviour rests on two quiet supports. The spin's hard to change. The beam is hard to smear. A single rounded number can hold the scale shift. About 20 kilometres across is a small span for an object with stellar mass. That small span makes gravity steep. It also makes the moment of inertia compact. A compact moment of inertia helps stabilise rotation. The everyday comparison stays simple. It resembles a heavy flywheel made small. The smaller and denser it is, the harder it is to nudge off rhythm. The third concept is torque and spin down introduced softly. Torque is a twist that changes rotation. A pulsar loses energy as it emits radiation and particles. That loss produces a gradual slowing. The slowing is usually smooth. It can be measured as a steady drift in the tick interval. The drift is tiny compared with the interval itself. The payoff is clear. A predictable drift can be modelled and removed. What remains can be extremely stable. The main limit of observation appears with a gentle boundary. The interior cannot be observed directly. The beam is the only accessible messenger. Inference must connect timing changes to internal changes. That connection has uncertainty. Small irregularities can come from the magnetosphere rather than the interior. Small changes along the path can mimic a change at the star. The limit is specific. Timing measures arrival intervals. It does not measure the surface pattern directly. It cannot resolve whether a slight shift comes from beam shape change or true spin change without long context. Over many pulses, patterns separate. Short noise averages away. Slow trends remain. The sense of clock emerges from patience rather than immediate certainty. Another visual anchor slows the pace. The surface is imagined as a dark lacquered sphere with a thin frost-like crust. A polar cap glows faintly. A narrow rim marks the open field boundary. The rim is a physical detail. It is a boundary line in geometry and it defines the beam footprint. As the sphere spins, the rim sweeps past the same direction again and again. The pulse returns with a familiar shape. The analogy for this section is new and singular. The structure resembles a ceramic bell hanging in still air. When struck, the bell rings with a stable tone. The tone persists until energy fades. The tone can shift if the bell warms or cracks. A neutron star is not a bell, yet its rigid structure supports stable modes and stable rotation. The clock-like tick is the tonal steadiness translated into time spacing. The scale shift becomes calm and wide. A crust layer can be thin compared with the radius. The magnetosphere can extend far beyond the star. The pulse spacing can be a fraction of a second, yet it can remain predictable across years. The mind moves from a cap only kilometres wide to a beam travelling light years. The same geometry repeats without needing a visible image. The closing transition stays soft. With the compact engine set, the next section can linger on rotation itself as a clock. It can show how geometry turns a spin into a repeating arrival pattern. A steady clock in space begins as a simple act of turning that refuses to blur. The pulse stays predictable because the rotation keeps a stable phase over immense counts. In that region, the star is so compact that its spin becomes a stored pattern rather than a fragile motion. The surface is nearly spherical. Any equatorial bulge is subtle. The crust is a thin shell over dense layers. Small surface bumps are flattened by gravity. That physical smoothness reduces irregular torques. The scene opens on a dark sphere turning in silence. A faint band of plasma curves above the surface like a dim halo. The band is not a ring of matter. It is a region where magnetic lines guide motion. The turning pulls that region around with it. The same orientation returns. The same beam geometry returns. The tick is therefore a repeat of orientation in time. The first concept is phase. Phase is the position within a repeating cycle. A pulse marks a particular phase of rotation. If the next pulse arrives with the same phase, the clock is consistent. A small shift in phase is a small timing error. The payoff is immediate. Timing does not require a picture of the star. It requires the repeated return of the same phase marker. The visual anchor slows and sharpens. A thin, bright arc appears at the edge of the polar region. It is a boundary where open magnetic lines begin. The arc sweeps around like a narrow brushstroke on a spinning globe. Each sweep sets a moment in time. The arc has a crisp edge. The edge makes the pulse rise quickly. That quick rise makes timing precise. The analogy for the section stays singular and calm. The rotation resembles a whirlpool in a still pond. The center holds steady. The spiral arms curve around it. A leaf drifts near the edge and circles again and again. The swirl keeps its rhythm even as the leaf wobbles. In a pulsar, the swirl is not water. It is the repeating geometry of field and beam. The leaf is not matter. It is the arrival time of a pulse. The rhythm persists because the center is hard to disturb. The second concept is moment of inertia. Moment of inertia is resistance to spin change from a given torque. A compact star concentrates mass near the center. That concentration can stabilize rotation. A small torque then produces a very small change in spin rate. The payoff comes quietly. The clock stays good because the same small disturbances produce only tiny drift. A single rounded number sets the scale of repetition. Some of the fastest pulsars turn about 700 times each second, like a swirl that completes hundreds of loops before a shadow shifts across a stone. Such speed does not make the clock louder. It makes the tick spacing short. Short spacing allows many ticks to be averaged. Averaging strengthens stability. The scene moves from one pulse to a long train of pulses. Each tick is ordinary. The power comes from counting. A signal would carry that count across the cold medium between stars. Each arrival adds another mark. Over a day, the count becomes enormous. Over years, tiny trends become visible. The rhythm becomes a ruler made of intervals. A new visual anchor appears far from the surface. A faint cylindrical boundary forms in imagination around the star. It is not a wall. It is a distance where corrotation would become too fast. Light cylinder is the radius where co-rotation matches light speed. The definition is brief and the meaning stays visual. Inside that radius, magnetic structure can rotate with the star. Outside it, the structure must open and stream outward. The boundary is a gentle limit. It shapes where the beam can remain organized. The analogy stays in nature. It resembles a calm eddy that holds together near its center. Farther out, the flow breaks into long streaks. The payoff is clear. A structured region helps keep the pulse shape steady. A steady shape helps keep the timing mark sharp. A second number can sit lightly as a scale shift. For a very fast spinner, the light cylinder can be a few hundred kilometers out like the broad span of a large thundercloud. The star itself is far smaller than that. The beam region is far larger than the star. The pulse then travels far beyond both. The mind moves from kilometers to light years without strain. The timing problem stays the same. It is the return of phase. It is the persistence of spacing. A limit of intuition arrives softly and it stays specific. Rotation seems like a perfect metronome in thought. Real pulsars show timing noise and sudden irregularities. Small changes in the magnetosphere can shift the pulse shape. A slight shift in shape can shift the measured arrival time. The limit is not a failure of the clock, it is a limit of inference. Timing is extracted from a shape that can vary. The underlying rotation can remain stable while the measured tick jitters. Separating those effects requires long baselines and careful modelling. The limit is also observational. The surface cannot be resolved. The beam cannot be watched as a moving spot in an image. Only the arrival pattern is available. That pattern is a one-dimensional record. It carries ambiguity. A small delay could come from path changes in interstellar plasma. It could come from beam geometry changes. It could come from a true change in spin. The payoff is practical. A stable clock emerges when the repeating pattern is fit across many pulses. Short-term jitter averages away. Long-term drift becomes measurable. The process resembles watching ripples on a pond when a steady spring feeds water from below. The surface trembles in wind. The tremble is noise. The steady input is the source. Over time, the average height reveals the source flow. In pulsar timing, the average phase reveals the true rotation. The visual anchor returns to the boundary arc on the polar cap. The arc sweeps with each turn, the arc stays in the same place on the surface. That fixed place is a physical detail. It is a rim set by field geometry. The rim sets the beam footprint. The beam footprint sets the pulse profile. The profile sets the timing mark. Each link is quiet and mechanical without machinery. Another checkpoint deepens the sense of controlled escalation. A pulse train is treated as a long thread of evenly spaced knots. Each knot is a phase marker. If a knot arrives early, a cause exists. If many knots drift together, a trend exists. The payoff comes gently. Timing becomes a tool for finding small effects in a large universe. The effects are not announced. They appear as tiny shifts in a steady pattern. The scale shift widens again. A single tick can be shorter than a blink. The same object can remain a reliable reference across decades. The beam crosses regions of gas and dust that change slowly. The star continues to turn beneath that changing medium. The steadiness is not absolute. It is relative to the calmness of the rotation and the predictability of its drift. The closing transition stays soft. With phase and rotation set as the core clockwork, the next section can linger on how beams form in detail. It can show why a narrow beam produces a clean timing edge. The pulse becomes a clock only after a beam becomes narrow enough to leave a clean edge in time. The beam is narrow because strong magnetic geometry funnels motion into a thin cone. In that region, the star's rotation carries a fixed pattern of field lines past the same direction again and again. The scene begins close to the surface. A polar cap sits like a small oval patch on a dark sphere. Its rim is sharp. Just above it, a thin layer of plasma forms a faint luminous skin. The skin has a brightness gradient. It is brightest near the cap's center and softer toward the rim. The first concept is magnetic inclination. Magnetic inclination is the tilt between magnetic and spin axes. If the tilt is small, the beam sweeps a small circle. If the tilt is larger, the sweep can cross many directions. The payoff arrives quickly. A tilt turns rotation into a sweeping signal that can pass a distant line of sight. The visual anchor slows and steadies. A narrow hollow cone of emission extends outward from the polar region. The cone is not filled evenly. Its inner edge is dim, its outer edge is brighter like a thin ring of light. As the star turns, the ring sweeps through space. When the ring edge passes a distant direction, the pulse rises sharply. When the edge leaves, the pulse falls. Sharp edges produce sharp timing marks. The second concept is beaming geometry. Beaming geometry is the shape and direction of emitted radiation. A beam can act like a rotating stencil. The pulse profile becomes the imprint of that stencil across time. A clean imprint repeats cleanly. The section's analogy stays singular and quiet. The beam sweep resembles a thin slit of sunlight moving across a dark room through a slowly turning shutter. The wall stays still. The slit moves. When the bright line crosses a fixed point, illumination appears abruptly. When it moves away, darkness returns. In a pulsar, the wall is not a wall. It is a distant direction in space. The shutter is not wood. It is magnetic structure turning with the star. The payoff is immediate. The timing mark is the moment the bright edge crosses, not the whole glow. The scene shifts upward above the cap. The plasma layer is not thick. It is a compact region where particles accelerate and emit. About 1 kilometer in height is a useful scale like the height of a tall mountain. That small height matters because it fixes the curvature of the beam near its source. A small source region limits wandering. It also limits smearing. A signal would then carry a stable pulse shape far beyond the star. A second visual anchor appears along the cone. The cone's brightness is not uniform. It has a thin, bright arc where particle density peaks. It has a softer wake where emission fades. As rotation continues, that arc becomes the leading edge of the pulse. The wake becomes the trailing edge. The pulse is therefore a map of structure in the cone. The payoff arrives with calm clarity. The pulse is not a random flicker. It is the rotating beam's internal texture translated into time. At this distance, the motion is never seen directly. Only the repeated timing and the repeated shape appear. The gentle escalation continues into a checkpoint about stability. A narrow beam is sensitive to small changes in direction, yet the same strong field that creates the beam also stabilizes it. The field lines are anchored in dense matter beneath the crust. That anchoring reduces wandering of the emission footprint. The rim of the polar cap remains sharply defined. The beam therefore returns with similar orientation. The next visual scene slows again. A faint curtain of interstellar dust drifts in a broad sheet. The sheet is not opaque. It is a soft veil with subtle lanes. The beam passes through and leaves only a slight attenuation. The pulse still arrives as a crisp edge, then a fading tail. The rhythm holds, another payoff lands softly. Even when the path contains a veil, a sharp edge can remain measurable because it is a time marker rather than a brightness measurement. The limit of observation enters with a specific boundary. The beam shape cannot be mapped in 3 dimensions from a single line of sight. Only a one-dimensional cut through the beam is available as the pulse profile. Different beam shapes can produce similar profiles. A slight change in plasma distribution can mimic a shift in beam direction. This is a limit of inference. Timing relies on fitting a model pulse shape to arrival data. If the shape changes, the measured arrival time can shift even if rotation does not. Another limit appears in the source region. The plasma layer is dynamic. Density and acceleration can vary. Those variations can alter the leading edge steepness. A steeper edge yields a cleaner timing point. A softer edge increases uncertainty. The payoff remains practical. Long averaging and careful alignment of profiles can separate true phase drift from shape drift. The section returns to physical details to keep the sense concrete. The polar cap rim is a boundary between closed and open field lines. The boundary is like a contour line on a globe. It defines where particles can stream outward. The open region forms a bundle. The bundle flares with distance. That flare gives the cone its hollow ring appearance. The ring's outer edge stays the most reliable timing feature. It produces the fastest change in brightness across time. Another visual anchor appears far from the star. The cone sweep traces a circular path across empty space. The circle is vast compared with the cap, yet it is still a controlled motion. The beam crosses the same distant direction with each rotation. The repetition turns geometry into timekeeping. The analogy returns once more without adding new ones. The moving slit stays narrow. It stays clean. It paints the same line at the same intervals. The paint is not colour. It is arrival time. The scale shift widens with calm steadiness. A layer only a kilometre high shapes a signal that can remain recognisable across light years. A turning period shorter than a heartbeat can define a reference across decades. The mind moves from a thin plasma skin to a galaxy-sized path without strain. The final checkpoint steadies the arc. A beam creates a pulse. A sharp pulse creates a stable timing mark. A stable timing mark allows tiny deviations to stand out against a predictable background. The closing transition stays gentle and forward. With the beam's geometry set, the next section can linger on the pulse profile itself. It can show how shape, not just spacing, strengthens a cosmic clock. A pulse is not only a gap between ticks, the pulse is also a shape that returns with quiet consistency. In that region, timing becomes sharper when the same shape repeats with the same edges. The scene begins as a thin line drawn in time. The line rises quickly. It forms a rounded crest. It falls into a long, soft tail. The crest is not perfectly smooth. A small shoulder appears on one side, a faint notch appears on the other. These details are physical in origin. They come from gradients in brightness across the beam. They come from the beam's hollow rim and softer interior. As rotation continues, the same shoulder returns, the same notch returns. The first concept is the pulse profile. Pulse profile is the brightness pattern across one rotation. The profile acts like a fingerprint in time. It contains a steep leading edge. It contains a slower trailing edge. The payoff arrives at once. A steep edge pins a consistent arrival moment. The second concept is time of arrival. Time of arrival is the best estimate of a pulse's arrival time. The estimate is not taken from the brightest point alone. It is taken from how the whole shape aligns with itself. A signal would arrive with small noise on top of the shape. The noise can shift the peak slightly. The steep edge stays more reliable. The profile alignment uses the stable parts of the shape. That turns a flicker into a measurement. The visual anchor slows into a calm sequence. A ribbon of faint emission extends along open field lines. Along that ribbon, brightness changes in layers. A bright band sits near the outer rim. A dimmer band sits inside. The bands curve outward as distance increases. When the beam sweeps across a distant direction, the outer bright band crosses first. A sharp rise appears, then the inner band follows, a gentle plateau appears, then the bands move away, a long tail appears, the profile becomes a map of layered emission. The map repeats because the layers repeat. The section's analogy stays singular and natural. The pulse profile resembles a wave train on a wide, dark lake. Some waves have a crisp front and a longer backwash. A small notch can appear when two ripples overlap. The notch returns if the lake bed and wind stay steady. In a pulsar, the lake is not water. The repeating ripples are patterns in emission. The notch returns because geometry returns. The payoff comes quietly. The clock improves when the whole wave shape is used, not only the spacing. A single rounded number anchors the scale. A typical pulse feature can be about 1/1000th of a second wide, like the brief flicker of a deep sea glow that fades before a fin completes a stroke. Such narrowness matters because it reduces ambiguity. The narrower the edge, the less time uncertainty spreads. The scene shifts from one pulse to many. A long train of pulses arrives with small variations. Some pulses are slightly brighter, some are slightly dimmer. The shoulder shifts by a tiny amount. The notch softens for a moment. Yet the average profile remains. Averaging is a calm act. It builds a stable template from many repeats. The template is a smooth version of the profile. It holds the steep edge, it holds the shoulder, it holds the tail. The payoff lands with clarity. A stable template allows each new pulse to be compared against a fixed reference. That comparison turns many noisy arrivals into a precise rhythm. Another visual anchor appears in the space between the star and distant regions. The signal crosses a thin fog of free electrons. The fog is not uniform. It has gentle clumps and voids. The clumps stretch the pulse. The stretching creates a scattering tail. The tail is a physical detail. It is a gradual fade caused by multiple paths through the medium. The leading edge can remain sharp while the tail grows longer. Light behaves as a wave that can scatter from small irregularities. The profile therefore carries both source structure and path structure. The payoff is practical. The leading edge is often less affected than the far tail. Timing can lean on the part of the profile that stays stable. The limit of observation enters with specific boundaries. The star cannot be resolved into a disk. The beam cannot be watched as a moving spot. The only record is the sequence of arrival times and shapes. The shapes vary because the emission region is dynamic. Plasma density can change from one rotation to the next. That intrinsic variability is a limit of measurement. It adds jitter to the pulse shape. Jitter makes the alignment less certain for a single pulse. A second boundary comes from propagation. The electron fog changes along the path. That change can alter dispersion and scattering. If the profile is stretched differently, the alignment can shift. This is a limit of inference. A shift in measured arrival time can come from shape change rather than true spin change. Separating these requires long baselines. It requires careful modelling of how the profile evolves with frequency and time. The payoff remains calm. When enough pulses are combined, random variations wash out. The stable part of the profile remains. That stable part becomes a clock hand in time. The narrative moves through another checkpoint about consistency. A good pulsar clock is not perfect because each tick is identical. It is good because deviations are trackable. If a drift appears in the time of arrival series, it can be compared against known profile changes. If the profile stays steady and arrival times drift, the drift is more likely to reflect true phase change. If the profile changes while arrival times shift, the shift may be partly apparent. The payoff is immediate. The profile acts as a guardrail for interpretation. Another visual anchor slows the pace again. The polar cap rim remains a thin boundary on the surface. The boundary maps to an outer beam rim in the magnetosphere. That outer rim produces the steep edge in time. The steep edge is like a clean shoreline against a dark sea. A small tide can change brightness. The shoreline position stays. The profile's steep edge therefore stays stable even when the crest height varies. The analogy does not multiply. The lake wave remains the only main comparison. The wavefront stays the timing marker. The backwash is secondary. The mind shifts scale gently. A feature on a profile lasts 1,000th of a second. The magnetosphere structure that creates it spans thousands of kilometers. The path that stretches it can span light years. Yet the same steep edge can be identified across years of repeating cycles. The clock is therefore not a single tick. It is a pattern recognized over immense repetition. The payoff arrives with a soft sense of completion. The reason a pulsar can keep time is not only the spin, it is also the repeatable shape of the beam sweep. The shape provides a still marker within each rotation. It allows phase to be tracked with fine resolution. The closing transition stays gentle. With pulse shape established as a second pillar of timing, the next section can turn towards slow changes in the clock itself. It can show how spin down appears as a smooth drift rather than a sudden break. A good clock can slow down and still remain a good clock. The pulse stays useful because the slowing is usually smooth and predictable. In that region, the star loses rotational energy in a steady leak, rather than a sudden spill. The scene begins with a quiet sweep of the beam and a thin wake beyond the magnetized zone. A faint sheet of plasma stretches outward. It undulates gently like a ribbon in a slow current. Along that sheet, brightness is not a uniform. A sharp boundary appears where the flow changes direction. The boundary holds a thin gradient. The gradient marks where fields open and particles stream away. This physical structure is not decorative. It is the place where rotational energy turns into outward flow. The first concept is torque. Torque is a twist that changes rotation rate. In a pulsar, torque comes from electromagnetic stresses and escaping particles. The torque is small compared with the star's stored spin. That imbalance is the reason the clock changes slowly. The payoff is immediate. A small torque produces a slow drift that can be modelled as a smooth trend. The visual anchor stays close to the polar region. The cap rim remains a crisp edge on the surface. Above it, a thin accelerating layer glows faintly. Particles move along open lines and carry energy outward. The beam still forms, the beam still sweeps, yet each sweep takes a slightly longer time as years pass. The second concept is spin down. Spin down is gradual lengthening of the rotation period. The lengthening is tiny from one day to the next. It becomes visible only across vast counts of pulses. The payoff arrives softly. A slow drift can be removed from timing data, leaving a cleaner residual rhythm. A single rounded number anchors the scale. For some pulsars, the tick can lengthen by about 1 second over about 1,000,000 years, like adding a single extra blink across an age longer than mountains remember. That comparison turns an abstract drift into a quiet sense of smallness. The drift is real, yet it is gentle. The scene widens outward from the star to the streaming region. The plasma sheet beyond the rotating magnetized zone is not perfectly smooth. It has a wave-like fold. The fold repeats because rotation repeats. The fold forms a spiral pattern that slowly unwinds into interstellar space. The spiral is faint. Its edges are defined by subtle gradients rather than sharp walls. Light behaves as a messenger that can trace those gradients through changes in the pulse. The payoff is practical. The outward flow provides a physical reason for the clock to slow, and the regularity of that flow supports regular slowing. A new visual anchor appears as a faint widening cone of particles that thins with distance. The cone is not a solid object. It is a region where density falls outward. Near the star, the density is higher. Farther away, the density fades into the background medium. The edge of the cone is a boundary of motion. Inside particles stream outward along open lines. Outside, the medium remains nearly still. This boundary is another physical detail that helps timing. It changes slowly. It does not flicker wildly from one rotation to the next. Another payoff arrives. Slow structural change tends to produce slow timing change. That is the kind of change that can be predicted. The analogy for this section stays singular and natural. The slowing resembles a river that carries a calm whirlpool downstream. The whirlpool keeps turning while it drifts. It also weakens as water leaks into the wider flow. The turning persists. The weakening is gradual. In a pulsar, rotation is the whirl. Outflow is the leakage. The clock is the persistence of turning despite the slow loss. The narrative moves through a checkpoint about what timing actually measures. Timing tracks phase across many rotations. A slow drift in phase can be fit with a simple curve. Removing that curve is not a trick. It is recognition of the known physical process. The payoff is clear. A clock does not need constant speed to be useful. It needs a predictable change in speed. The scene returns to the pulse profile because profile stability protects the measurement. The leading edge remains steep. The trailing edge remains soft. The steep edge provides a consistent marker even as the period drifts. The marker shifts in absolute time, yet it stays consistent relative to the rotation cycle. Another visual anchor appears in the surrounding medium. A diffuse cloud drifts across the line of sight. The cloud is not dense. It is a faint veil with a smooth gradient of free electrons. As the pulse passes through, the profile stretches slightly. The stretching is slow, can change over months or years. This introduces a limit of observation. The measured arrival time is not a pure readout of rotation. It is a readout after propagation through a changing medium. The limit is specific. Dispersion and scattering can shift the apparent pulse time by altering the shape. The shift can mimic a change in spin if it is not accounted for. A second limit appears in the source. The magnetosphere can change state. The accelerating layer above the cap can shift in density. That can nudge the profile edge. That nudging can move the measured arrival moment even if phase remains stable. This is a limit of inference. The data provide a one-dimensional time series. The underlying system is three-dimensional and dynamic. Separation of causes requires long baselines and careful comparison of profile shape over time. The payoff remains calm. When those limits are respected, the smooth spin-down trend becomes a reliable background rather than a confusion. The story widens into a gentle scale shift. A single rotation can be less than a second. The slowing can be noticeable only across thousands of years. Over 1 million years, the change can still be modest for a stable pulsar. Across that span, the star remains compact, the polar cap rim remains sharply defined. The outward plasma sheet continues its slow, folded sweep. The clock is therefore a layered structure. Rotation provides the beat. The beam provides the marker. Spin down provides a predictable drift. The deeper reason this supports timekeeping is quiet. Predictability allows subtraction. Subtraction reveals smaller patterns. Another visual anchor slows the pace again. The folded plasma sheet is imagined as a thin curtain, and the curtain's edge catches faint emission as it twists. The twist is not random, it is carried by rotation. Even as rotation slows, the twist remains coherent. The scene holds that coherence as a sign of stability. The payoff is simple. A coherent outflow suggests a coherent torque. A coherent torque suggests a smooth clock drift. The closing transition stays gentle. With spin down understood as a slow and modelable change, the next section can turn toward rarer interruptions. It can show how sudden shifts and internal coupling can appear without destroying the long-term rhythm. A clock can be steady for years and still show a sudden tiny step in its rhythm. The long-term timing stays strong because those steps are rare and often measurable. In that region, the star's interior can exchange angular momentum between layers, and the pulse train records the exchange as a small change in phase. The scene begins at the surface where the crust looks like a dark glaze under extreme gravity. The glaze is not smooth at microscopic scales. It holds a pattern of cracks and plates locked in place by pressure. Along the polar region, the rim of open field lines remains sharp. Above it, the emitting layer glows as a thin oval with a dim gradient toward the edge. The pulses arrive with a familiar spacing. Then the spacing shifts by a hair. The shift is not visible as a dramatic jump. It is a quiet correction that accumulates over many ticks. The first concept is a glitch. A glitch is a sudden change in rotation rate. The change is usually an increase in spin, not a decrease. The payoff is immediate. A glitch shows that the clock is not only a surface phenomenon, it is a coupled system with hidden reservoirs of spin. The second concept is internal coupling. Internal coupling is exchange of rotation between layers. A neutron star is not a single rigid wheel. It contains a crust and deeper components that can rotate slightly differently. The deeper component can store angular momentum. When coupling strengthens, suddenly some stored spin can move into the crust. The crust then spins a little faster. The pulse arrives slightly early compared with the prior trend. The visual anchor shifts inside the star without naming inaccessible details too sharply. A layered interior is imagined as concentric shells. The outer shell is the crust. Beneath it lies a region that can flow without friction in certain conditions. The boundary between shells is not a sharp wall. It is a transition zone. In that zone, pinning and unpinning can occur. Pinning is locking of vortices to the crust lattice. Vortices are thin tubes of rotation in a superfluid. The definition stays brief and the imagery stays gentle. The star's rotation in the deep layer is carried by many such tubes. Some tubes can stick to the crust lattice. If many release at once, the deep layer can share spin with the crust. The payoff arrives with calm clarity. A sudden timing step can arise from a collective release in the hidden rotation structure. A single rounded number anchors the scale of the event. A typical glitch can change the rotation by about 1 part in a million, like adding 1 extra grain to a million grain line, and still noticing the difference by careful counting. The comparison keeps the magnitude soft and safe. The change is tiny, yet timing can detect it because the pulses repeat so many times. The scene moves outward again to keep the breath steady. The pulse profile remains recognizable. The steep leading edge remains steep. The trailing tail remains long and soft. After the glitch, the pulses align again, but with a slightly altered schedule. The long-term spin down continues. It resumes with a similar slope. The clock has stepped onto a nearby track and continues forward. The payoff is simple. A glitch does not erase the usefulness of the clock. It becomes an event that can be modelled as an offset plus a recovery. A new visual anchor appears in the magnetosphere. The plasma sheet beyond the star shows a subtle kink, as if a thin ribbon momentarily tightens. The kink is not a physical twist that can be watched directly. It is an imagined marker for how the field responds to a small change in rotation rate. A signal would then carry a slightly different phase schedule outward. The beam sweeps across the same directions. It does so with a barely altered cadence. The pulse train therefore becomes a record of interior and exterior together. The analogy for this section stays singular and quiet. The glitch resembles ice on a slow river. The surface appears steady. Beneath water flows and builds pressure behind a snag. When the snag releases, the surface lurches by a small amount. The river then returns to steady flow. In a pulsar, the crust is the surface ice. The deeper layer is the flow. The release is the coupling event. The payoff remains clear. A sudden step can occur without destroying the overall predictability. The limit of observation arrives with specific boundaries. The interior cannot be seen. Only timing changes and profile changes are measured at a distance. A glitch can be identified from the pulse arrival series, yet the detailed mechanism cannot be uniquely determined from timing alone. Several internal models can fit a similar step in recovery. This is a limit of inference. The clock reveals that something exchanges angular momentum. It does not reveal exactly how many vortices move or where. Another observational limit appears in cadence. If pulses are not recorded continuously, a step can be missed or smeared. A gap in observations can blur the exact glitch time. That blur can spread uncertainty into the recovered model. The payoff stays practical. Long-term timing gains power from continuous sequences. It also gains power from stable profiles that allow consistent alignment across years. Another visual anchor slows the pace again. The crust lattice is imagined as a tiled pattern under immense pressure. The tiles are small. The pattern is dense. A fracture line is a boundary that can hold stress. The stress changes slowly as the star spins down. In rare moments, stress reorganizes and coupling changes. The pulse train records the result as a tiny phase step. The physical detail is the boundary itself, a line where structure differs. That boundary is a place where pinning can differ from its surroundings. The story moves through another checkpoint. Glitches show that pulsars are not perfect atomic clocks. They are physical clocks with internal dynamics, yet atomic clocks can suffer environmental shifts and systematic drifts. Each type of clock has its own noise. The pulsar's noise includes occasional steps. The payoff is calm and reassuring. The steps are small. The steps can be fit. The clock remains useful because the long baseline absorbs rare events. The scale shift widens gently. A glitch happens in an instant. Its consequences persist in the phase record for years. The interior event takes place across microscopic distances in a lattice. The phase shift is traced across light years as a change in arrival schedule. A tiny internal adjustment becomes a measurable signature across cosmic distances. The closing transition stays soft. With sudden steps and internal coupling set into the timing picture, the next section can return to the path between star and distant observer. It can show how the interstellar medium adds slow distortions that must be separated from true clock changes. A pulse can leave a star perfectly on time and still arrive with a gentle delay shaped by the space it crosses. The clock remains strong because the delay follows stable rules that can be tracked and removed. In that region, interstellar space is not empty. It is a thin mixture of ions, electrons, and dust. The scene begins far from the star where a cold cloud drifts like a translucent veil. The veil has soft lanes and knots. Its density changes slowly across long distances. A signal would pass through this veil and feel it as a slow reshaping rather than a blockage. The pulse enters as a crisp edge. It exits with a stretched tail. The physical detail is the tail itself. It is a gradient in time caused by many slightly different paths through the medium. The first concept is dispersion. Dispersion is frequency-dependent delay through free electrons. Lower frequency waves are delayed more than higher frequency waves. The definition stays brief and the imagery stays calm. The pulse is like a ripple that travels through a layered gel. Some parts move more slowly through the gel. The payoff arrives quickly. If dispersion is measured, the original timing can be reconstructed from the delayed timing. The second concept is scattering. Scattering is pulse broadening from irregularities along the path. Small density variations act like tiny lenses. They send parts of the wave along slightly longer routes. The result is not a new pulse. It is a long afterglow after the main edge. The afterglow is the scattering tail. The payoff is clear. A steep leading edge can stay measurable even when the tail grows long. The visual anchor slows and sharpens. A long filament of gas lies along the line of sight. It has a bright boundary on one side and a softer interior. The boundary is a gradient where electron density changes. As pulses pass, their leading edge remains sharp. Their trailing edge stretches into a faint smear. The smear is longer when the filament is denser. It is shorter when the filament thins. The effect is gentle. It changes over months and years. The analogy for this section stays singular and natural. The propagation resembles light passing through a rippled pane of ice. The scene behind the ice is still visible. Edges remain. Fine details blur. A bright edge becomes a softened streak. In pulsar timing, the pulse is the bright edge. The interstellar medium is the rippled ice. The payoff lands softly. Even when the path blurs the pulse, the underlying rhythm can remain recoverable because the blurring is structured. A single rounded number anchors the scale of the effect. For some paths, the dispersion delay between a high tone and a low tone can be about 1 second, like the pause between distant thunder and the next gentle echo in a wide valley. The pause is not random, it is tied to the amount of free electrons along the route. That amount is called dispersion measure. Dispersion measure is an electron column along the path. The definition stays short and the meaning stays visual. It is the count of electrons stacked along a thin tube between source and receiver. The payoff is immediate. If the electron column is known, the delay can be predicted at each frequency. Another visual anchor arrives as a slow map through space. The line of sight passes through a spiral arm. It then passes through a quieter interarm region. Electron density is higher in the arm. It is lower between arms. The pulse delays therefore drift slowly, as the line of sight samples different regions due to relative motion through the galaxy. The drift is not a failure of the clock. It is a changing filter laid over the clock. The payoff is practical. Monitoring that filter allows correction, and the corrected timing exposes more subtle effects. The limit of observation enters with clear boundaries. The electron distribution cannot be directly imaged along the entire path. It must be inferred from how pulses arrive at different frequencies. That inference has degeneracy. Different distributions can produce similar total delay. This is a limit of modelling. The correction can remove the bulk delay, yet small residuals can remain. Another limit appears in scattering. Scattering depends on tiny irregularities that change with time. Those irregularities can add a random component to pulse broadening. The random component introduces timing noise that cannot be perfectly predicted. This is a limit of measurement. It sets a floor for how precisely a single pulse can be timed. The payoff stays calm. Averaging many pulses reduces random variations. Measuring across many frequencies improves the dispersion correction. The clock then re-emerges with greater clarity. The scene returns to a concrete physical detail in the pulse profile. The leading edge is steep because it corresponds to the beam rim. The rim stays sharp at the source. Dispersion shifts the whole profile in time by a frequency-dependent amount. Scattering adds an extra tail that grows at lower frequencies. These effects are separable because they imprint different shapes on the profile. The payoff arrives gently. The path distorts time, yet the distortion carries a signature that can be recognized. Another visual anchor slows the pace. A diffuse cloud boundary moves slowly across the line of sight. The boundary is not a hard wall. It is a smooth transition where electron density rises, then falls. As the boundary enters, delays increase. As it leaves, delays decrease. The timing series therefore shows a soft swell. The swell is not a change in spin. It is a change in propagation. The distinction matters for a clock. The payoff is clear. Identifying the swell prevents false conclusions about the pulsar's rotation. The scale shift widens without strain. Irregularities smaller than a planet can shape a signal crossing light years. A delay of a second can be laid over a rotation period far shorter than that delay. Yet the delay can still be removed if its frequency dependence is tracked. The clock is therefore a layered record. The star provides the cadence. The interstellar medium provides a slow lens. Timing is the act of peeling away the lens to reveal the cadence beneath. The analogy remains the rippled ice. The ice blurs edges but does not invent a new scene. In the same way, propagation can smear a pulse but does not create the underlying rhythm. The closing transition stays gentle. With the path effects now clarified as correctable distortions, the next section can widen into the calm geometry of motion. It can show how orbital motion and relativity add another layer to pulse arrival times. A pulse can arrive early and late in a repeating pattern when the source follows an orbit. The timing stays precise because the repeating pattern is a clean signature of motion and gravity. In that region, two compact objects circle a shared center with steady cadence. The scene opens on a wide, dark plane of space. Within it, an invisible oval track is traced by a neutron star. The track is not drawn by dust, it is drawn by repeated pulse delays. The delays form a smooth wave in time. When the star moves toward the line of sight, pulses arrive slightly earlier. When it moves away, pulses arrive slightly later. The physical detail is the oval itself. The oval has a closer side and a farther side. It also has a changing speed along the path. The star moves faster near the closer side of the oval. The first concept is Doppler shift in timing. Doppler shift in timing is change in arrival interval due to motion. The definition stays brief and the meaning stays gentle. A moving source compresses intervals in the direction of motion and stretches them in the opposite direction. The payoff arrives at once. A periodic timing wave reveals the orbit even when the bodies are not seen. The visual anchor slows and becomes specific. The orbit is imagined as a pale loop of frost in space, and the neutron star glides along it without sound. At one part of the loop bends tightly. At another part, it opens wider. Those bends represent changing distance from the center of mass. Each bend corresponds to a particular set of pulse arrival shifts. The pulse train becomes a ruler laid over the loop. A second visual anchor appears near the companion. The companion is not described as a visible star with features. It is a compact mass that warps space around it. The warp is a smooth bowl. The bowl has a steep inner slope and a gentle outer slope. As pulses pass near the companion, their path through curved space-time becomes slightly longer. The arrival is delayed. The delay repeats each orbit. The payoff remains calm. A repeating delay near conjunction points to gravity-shaping travel time as well as motion-shaping timing. The second concept is Shapiro delay. Shapiro delay is extra travel time through curved space-time. The definition stays within 12 words and the image stays soft. Light behaves as if it takes a longer route through a deep valley. The delay depends on how close the path passes to the companion. It also depends on the orbital geometry. The pulse arrival series therefore carries a gentle fingerprint of gravitational curvature. A single rounded number anchors the scale of orbital cadence. Some binary pulsars complete an orbit in about 8 hours, like the slow turning of a long weather front that reshapes a whole sky in a single night. 8 hours is long compared with a millisecond pulse. It is short compared with a year. This contrast forms a scale shift that stays quiet. The pulses provide fine ticks. The orbit provides the slow wave. Together they create a layered clock. Another payoff arrives. The orbit's timing wave allows measurement of orbital parameters with extreme precision. It also allows separation of intrinsic spin changes from motion-induced changes. The story moves through a checkpoint about separation. The arrival time record is a sum of effects. One part is the star's rotation and its slow spin down. Another part is the line of sight motion in the orbit. Another part is the gravitational delay near the companion. Each part has a distinct shape in time. The Doppler part is roughly sinusoidal for a near-circular orbit. The Shapiro part is a sharper delay near conjunction. This separation is not a trick of language. It is a property of the timing patterns themselves. The payoff is clear. Distinct timing signatures can be fit and subtracted, leaving smaller residuals. The analogy for this section stays singular and familiar. The timing pattern resembles a buoy on an ocean swell. The buoy rises and falls with a regular wave. Small ripples ride on top of that wave. The ripples are the pulse ticks. The swell is the orbit. When the swell is modelled, the ripples can be timed more cleanly. The buoy does not need to be seen. Its motion is inferred from the repeating rise and fall. In a binary pulsar, the clock is inferred from repeating early and late arrivals. The visual anchor returns to the oval loop. Along one arc, pulses arrive progressively earlier. Along the opposite arc, they arrive progressively later. The turning points are smooth. They mark where radial motion reverses. The physical detail is the smoothness of the turning points. Smooth turning suggests a stable orbit rather than chaotic motion. Another visual anchor appears near the companion again. The gravitational bowl deepens and then relaxes as the path angle changes. The delay curve is not symmetric. It depends on inclination. That asymmetry becomes an additional clue to geometry. The payoff arrives gently. Gravity and motion can be disentangled because they imprint different asymmetries in time. The limit of observation enters with clear boundaries. The orbit is not traced in an image. It is traced in timing residuals. This is a limit of inference. Different combinations of inclination and companion mass can produce similar delays over part of an orbit. Continuous timing over many orbits reduces that degeneracy, but it may not remove it entirely. Another limit comes from the interstellar medium. Slow dispersion changes can add additional timing wander. That wander can mimic slight orbital variations if not corrected. This is a limit of modelling. The remedy is multi-frequency timing and long data spans. The payoff stays calm. When limits are respected, orbital signatures emerge as clean periodic patterns. Another checkpoint widens the arc toward the title. A pulsar in a binary can serve as a clock and also as a probe of gravity. The clock is not ruined by motion. Motion becomes part of the clock model. Once the model is applied, the remaining timing can be extraordinarily stable. That stability can rival laboratory time standards over long baselines. The scale shift widens again. A pulse tick can be 1,000th of a second. An orbital cycle can be hours. Changes in orbital period can unfold over years. The same data stream holds all these scales at once. The closing image slows and settles. The oval track fades into darkness, but the timing wave remains in the sequence of arrivals. The gravitational bowl remains implied by a repeating delay near conjunction. With motion and gravity now part of the timing story, the next section can widen further into relativistic consequences over long spans. It can show how tiny timing trends accumulate into deep tests of time itself. A timing record can feel like a simple list of arrivals until gravity quietly reshapes the meanings of time itself. The pulses keep their value because relativity adds patterns that are stable and modelable. In that region, motion and gravity do not merely move objects. They also change the rate at which time accumulates along different paths. The scene opens on an orbital plane that is dark and empty. Within it, two compact masses trace an ellipse around a shared centre. The ellipse has a narrow end and a wide end. Near the narrow end, the separation is smaller. Gravity is stronger. Speed is higher. Near the wide end, separation is larger. Gravity is weaker. Speed is lower. The physical detail is the changing curvature of the orbit. The orbit bends more tightly near the narrow end. That tight bend produces a distinct timing signature. The first concept is time dilation. Time dilation is slower time in gravity or at high speed. The definition stays brief and the effect stays visual. A clock deep in a gravitational bowl runs slower than a clock on the rim. A clock moving fast also runs slower compared with a slower one. In a binary pulsar, the pulsar clock is carried through both conditions each orbit. The payoff arrives quickly. The orbital timing curve is not only a Doppler wave, it also carries a change in the pulsar's intrinsic ticking rate across the orbit. The visual anchor slows and sharpens. The gravitational bowl around the companion is imagined as a smooth depression. The pulsar passes near the depression's steep side at periastron. Periastron is the closest orbital point. The definition remains short and the meaning stays clear. Near this point, the path arcs tightly. The surrounding space is more curved. The pulsar's speed is also higher. Both effects combine. The pulses do not only arrive early or late due to distance changes, their spacing can also shift slightly because the pulsar's own clock rate changes during the close pass. The payoff is calm. Relativity makes the pulsar's ticks compress and relax in a repeatable way tied to orbital phase. The second concept is periastron advance. Periastron advance is slow rotation of an orbit ellipse. The ellipse does not stay fixed in space. It turns gradually. The turning is small each orbit. It accumulates across many orbits. The visual anchor becomes a faint chalk-like ellipse that slowly rotates on a dark plane. Each time the pulsar returns to the closest point, the location of that point is slightly shifted. The pulse arrival pattern reflects that shift. The payoff is immediate. A turning ellipse changes the timing wave's phase and shape in a predictable long-term trend. A single rounded number anchors the gentle scale of this effect. In some relativistic binaries, the ellipse can rotate by a few degrees per year, like the slow turn of a compass needle over the course of a season. The comparison keeps the motion soft and familiar. The effect is subtle, yet pulses provide so many ticks that the subtle becomes measurable. The story moves through a checkpoint about layered signatures. The arrival times carry at least 3 orbital patterns. There is the Doppler shift from motion along the line of sight. There is the Shapiro delay from light travelling through curved space-time near the companion. There is the Einstein delay, which combines gravitational time dilation and special relativistic time dilation across the orbit. Einstein delay is change in clock rate across the orbit. The definition stays within 12 words. The payoff follows gently. Each pattern has a distinct shape in orbital phase, and the combination can be fit with high precision. The visual anchor shifts to the pulse train itself. Imagine a long thread of ticks. Over each orbit, the thread gently bunches and then spreads even after Doppler is accounted for. The bunching corresponds to slower or faster accumulation of proper time along the pulsar's path. Proper time is time measured along an object's world line. The definition stays short and the word remains calm. Proper time is the pulsar's own clock time. The timing model relates proper time to arrival time at a distant reference. The payoff is clear. The pulses act as marks of proper time that can be transported through curved space-time and motion. The analogy for this section stays singular and quiet. The relativistic orbit resembles a pendulum moving through honey and air in a repeating cycle. In honey, motion slows and the swing rate changes. In air, motion speeds up and the swing rate changes again. The pendulum keeps swinging. The environment changes the rate in a predictable way. In the binary, gravity and speed play the role of the changing medium. The clock remains the pulsar's rotation. The payoff remains calm. Predictable rate changes add information rather than destroying it. The limit of observation enters with specific boundaries. The system is not watched directly. Only arrival times are recorded across long spans. Several relativistic parameters can trade off against each other in a fit. Inclination and companion mass can both influence Shapiro delay. The distribution of interstellar electrons can introduce slow delays that mimic orbital effects if not corrected. This is a limit of modelling. It requires multi-frequency data and long observation spans. Another limit appears in intrinsic noise. Glitches and magnetosphere state changes can shift phase. Those shifts can confuse orbital parameter estimation if they coincide with sparse data. This is a limit of measurement cadence. Continuous data reduce confusion. Long baselines average away short-term noise. The payoff stays gentle. When these limits are managed, the timing model becomes a precise map of motion and gravity. The visual anchor returns to the rotating ellipse. Over many orbits, the ellipse slowly turns. The closest point migrates along the orbital plane. The pulses trace this migration as a slow drift in the timing residual pattern. The physical detail remains the ellipse itself with its narrow end. The narrow end is the place where relativity speaks most strongly because gravity and speed peak together. The scale shift widens softly. Each pulse tick can be 1,000th of a second. The orbital cycle can be hours. The periastron advance unfolds over years. The same pulse train connects all these scales into one record. A tiny change in clock rate during a close pass can be extracted from millions of ticks. A slow rotation of the ellipse can be traced across thousands of orbits. The closing transition stays gentle and forward. With relativity now written into the timing pattern as stable signatures, the next section can widen to an even longer baseline effect. It can show how orbital energy loss and slow period changes appear as a gradual reshaping of the orbit itself. A clock can whisper that an orbit is slowly shrinking even when the shrink is too small to picture. The pulses keep time well enough that a gradual loss of orbital energy becomes visible as a smooth trend. In that region, two compact masses circle and shed energy through gravitational radiation. The scene opens on the same dark orbital plane as before. The ellipse is still present. Its narrow end is still the closest approach. Yet the ellipse subtly tightens over time. The closest approach grows slightly closer. The far side grows slightly less far. The physical detail is the changing spacing of the timing wave's peaks. The peaks represent the same orbital phase. Their spacing in time becomes imperceptibly shorter. The first concept is orbital decay. Orbital decay is gradual shortening of orbital period. The definition stays brief and the meaning stays calm. The orbit loses energy. The period shrinks. The payoff arrives quickly. A shrinking orbit produces a predictable drift in pulse arrival patterns that can be tracked across years. The visual anchor slows into a gentle image. Imagine the ellipse drawn with faint chalk on black stone. Each orbit retraces the chalk line. Over many orbits, the chalk line is redrawn slightly inside the old one. The difference between lines is tiny. It is smaller than the width of the chalk. Yet the sequence of pulse timings can reveal it because the clock ticks so often. The second concept is gravitational waves. Gravitational waves are ripples in space-time carrying energy away. The definition remains short and the imagery stays soft. The orbit is not silent in gravity. It sends a faint ripple outward. The ripple is not a sound, it is a changing curvature that propagates. The payoff is clear. Energy carried away must come from somewhere and the orbit is the reservoir. The pulse train then becomes a ledger of that withdrawal. A single rounded number anchors the scale of long-term change. In some systems, the orbital period shortens by about a few microseconds per year, like shaving a single hair's breadth from the length of a day spread across an entire year. The comparison keeps the magnitude gentle and safe. It also highlights why a stable clock is needed. A microsecond is too small for intuition, yet it accumulates. Over a decade it becomes a larger shift. The scene moves through a checkpoint about accumulation. Each orbit produces a timing curve. The curve has a characteristic shape from Doppler motion. It has an additional feature from Shapiro delay. It has a modulation from Einstein delay. If the orbit decays, the phase of these features shifts gradually. The peaks arrive a little earlier than expected from a constant period model. The shift is not a one-time step. It is a growing offset. The payoff lands softly. A growing offset is a signature of a slow change in the orbit rather than a random disturbance. Another visual anchor appears as a thin spiral drawn in time. If orbital phase is plotted against time, the phase wraps around repeatedly. Orbital decay makes the wraps tighten. The spiral wins slightly faster. The spiral is not drawn on a screen. It is imagined from the sequence of arrivals. Light behaves as a messenger that preserves phase even as it travels. The pulses carry a stable tick count. The tick count allows detection of a tiny change in how quickly the orbit repeats. The payoff remains calm. The clock reveals not only what happens now, it reveals what changes slowly in the background. The analogy for this section stays singular and familiar. The decay resembles a slow drain of water from a basin that holds a rotating eddy. The eddy keeps spinning. The basin level falls. As the level falls, the eddy's radius shrinks slightly. The rotation cycle shortens a little. The change is too slow to notice moment by moment. Over many minutes it becomes clear. In the binary, the orbit is the eddy. Gravitational radiation is the drain. The pulse train is the repeated swirl count that reveals the shrink. The payoff is immediate. The same mechanism that carries energy away leaves a predictable signature that can be measured. The visual anchor returns to physical details of the orbit. Near periastron, the orbit bends tightly. That region experiences the strongest gravity and highest speed. It also contributes strongly to gravitational radiation. The tighter bend is therefore a physical feature linked to energy loss. Over time, the bend remains tight but occurs slightly more often because the orbit shortens. The pulses mark each occurrence. Another payoff arrives. The orbit's most relativistic phase becomes a repeated checkpoint for measuring long-term trends. The limit of observation enters with clear boundaries. Orbital decay is not measured by watching separation shrink. It is inferred from timing residuals against a model. Several effects can imitate a slow drift if not handled carefully. A change in dispersion along the line of sight can produce a slow timing drift. A change in pulse profile can shift measured arrival times. A small glitch can introduce an offset that looks like a trend if data coverage is sparse. This is a limit of inference. The remedy is a full timing model that includes frequency-dependent propagation and profile monitoring. Another limit appears in the baseline length. A microsecond per year effect requires years of data to stand out cleanly. Short baselines cannot separate long-term drift from noise. The payoff remains calm. When the baseline is long, the drift becomes a smooth curve that noise cannot mimic easily. Another visual anchor slows the pace again. The interstellar medium along the path is imagined as a broad fog sheet with soft lanes. The lanes drift slowly. Timing corrections remove the fog's dispersive delay. After correction, the remaining residuals show the orbital decay trend more cleanly. The trend is then attributed to gravity rather than the path. The physical detail is the fading, scattering tail that becomes more stable after correction. The pulse edges align more precisely. That improved alignment makes long-term orbital trends easier to detect. The scale shift widens gently. A microsecond is a tiny fraction of a second. A year is a vast count of pulses. A decade is a still larger count. Across that span, the orbit can lose enough energy to shift its period measurably. Across much longer spans, binaries can evolve dramatically. The pulses provide a stable ruler that links microseconds to decades. The closing image steadies. The chalk ellipse continues to be traced and the new line sits slightly inside the old. The change remains too subtle for an eye. It remains clear in a timing record because the record is built from countless ticks. The closing transition stays gentle and forward. With orbital decay now part of the long baseline story, the next section can widen beyond individual systems. It can show how networks of pulsar clocks can sense faint disturbances across the galaxy. A single pulsar is a clock. A quiet set of pulsars becomes a net that can sense a gentle bend in space-time across the galaxy. In that region, many pulse trains are compared against a shared timing model, and a common ripple can appear as a correlated drift. The scene opens far from any one star. Space is drawn as a wide dome with scattered points of pulsing light. Each point is not seen as a body. It is imagined as the steady beacon that marks time with repeated flashes. Between the points, the medium is dark and thin. A slow wave passes through the dome. The wave is not light. It is a mild stretching and squeezing of distances. The physical detail is a changing separation between imaginary grid lines in space. The grid lines become slightly farther apart in one direction. They become slightly closer in the perpendicular direction. The first concept is a timing array. Timing array is a set of pulsars timed together. The definition stays brief and calm. Each pulsar provides a time series of arrivals. The set provides many such series. If a disturbance affects space-time itself, the disturbance can imprint a pattern across the set. The payoff arrives quickly. A shared ripple can be separated from individual pulsar noise by looking for the same pattern in many places. The visual anchor slows and sharpens. Imagine a thin, invisible membrane stretched across the galaxy. The membrane has faint markings like latitude lines. Each pulsar sits at a different marking. When a slow ripple crosses the membrane, the marking shifts slightly. The pulses do not change at the source. The travel times through the membrane change. Some paths lengthen, some shorten. The arrival times therefore drift in a coordinated way. The second concept is correlation. Correlation is shared timing pattern across many pulsars. The definition remains short. It is the same drift appearing in multiple records with a predictable relationship to sky position. The payoff remains calm. Correlation is the difference between a local glitch and a global spacetime signal. A single rounded number anchors the scale of the slow ripple. The ripple can have a period of about 10 years, like a slow ocean swell that takes an entire decade to lift and lower a coastline. 10 years is long compared with any pulse period. It is also long compared with a day. This scale shift keeps the feeling gentle. The pulses provide fine ticks. The ripple provides a slow modulation. The story moves through a checkpoint about what is actually measured. Each pulsar has its own spin-down trend. Each has its own timing noise. Each line of sight has its own dispersion changes. These effects are mostly uncorrelated between different sky directions. Gravitational wave background would not be uncorrelated. It would produce a sky-dependent pattern in residuals. Residuals are timing differences after a model is removed. The definition stays short and the meaning stays clear. The payoff is immediate. Removing known trends leaves a quieter field where a common pattern can stand out. Another visual anchor appears as a set of long, thin threads. Each thread represents one pulsar's residual series. The threads are laid side by side in imagination. Most threads wander in their own way. Then a gentle bend appears in many threads at once. The bend is not identical in sign for all threads. Some bend upward, as others bend downward. The pattern depends on angular separation on the sky. The physical detail is the matched curvature of those bends. It is a slow, smooth curve rather than a sharp kink. Smoothness matters. A smooth curve suggests a long wavelength phenomenon rather than an instrumental artifact. The payoff is quiet. A long wavelength disturbance produces slow, coherent timing changes rather than sudden jumps. The analogy for this section stays singular and familiar. The array behaves like a set of buoys spread across a wide bay. Each buoy bobs with local chop. A long swell passes and lifts many buoys together in a patterned way. Some buoys rise slightly earlier than others because of geometry. The swell is the shared cause. The chop is local noise, the payoff is clear. The long swell can be recognized by comparing buoys rather than staring at one. The narrative continues through a controlled escalation. The timing array needs pulsars with stable profiles. It needs long observation spans. It needs careful correction of dispersion. It needs a consistent clock reference, yet the concept remains simple. A gravitational ripple changes the travel time of pulses. That change is written into arrival time residuals. Many pulsars provide many lines through the ripple. Together, those lines allow inference of the ripple's presence. The payoff remains calm. Multiplicity converts weak signals into detectable patterns. The limit of observation enters with clear boundaries. The ripple is not observed directly as a wavefront. It is inferred from residuals that also contain red noise from spin irregularities. Red noise is stronger at long time scales. The definition stays short. It means slow wander can dominate over fast jitter. That slow wander can imitate a long period ripple if not modelled. This is a limit of inference. Another limit arises from imperfect knowledge of the interstellar electron content. Slow dispersion changes can introduce decade-scale drifts in single pulsars. Those drifts are not correlated between widely separated sky directions. Yet if the sample is small, chance similarities can confuse detection. This is a limit of statistics. The payoff stays practical. A larger array and longer baselines reduce confusion by strengthening the expected correlation pattern. Another visual anchor slows the pace again. The galaxy is imagined as a faint disk with spiral lanes. Pulsars are sprinkled through the disk. A slow space-time ripple passes across the disk like a gentle tension shift in a fabric. The fabric does not tear. It stretches and relaxes. The pulse trains that cross the fabric change their travel times. The change is small, the repetition is enormous. That combination is what makes the method plausible. The payoff is simple. A weak effect can be detected if a clock is stable and repeated enough. The scale shift widens further. A millisecond tick is compared across years. A decade scale ripple is compared across many sky directions. A phenomenon that involves vast masses and distances is sensed through microsecond-level arrival changes. The mind moves from tiny timing marks to galactic scale patterns without strain. The closing image steadies. The buoys in the bay continue to bob, the long swell passes slowly. It is not dramatic. It is recognizable by patience and comparison. In the same way a pulsar timing array listens for a slow space-time rhythm by aligning many quiet clocks, the closing transition stays gentle and forward. With the idea of a galactic scale clock network now in place, the next section can return to the individual clock again. It can show why some pulsars achieve extreme stability and what limits that stability over decades. A pulsar can look steady from far away while its magnetosphere quietly shifts the shape of each pulse. The clock stays useful because the shape changes often follow recognizable modes that can be tracked. In that region, the timing precision is not only limited by rotation, it is also limited by how consistently the same part of the beam is sampled each turn. The scene opens close to the star without placing any instruments nearby. A dark sphere turns. Near its magnetic pole, an emission zone forms a thin ring. The ring is brighter along one arc and dimmer along another. The arc is a physical detail with a gradient. It is not a uniform circle. As the star rotates, the ring sweeps past the line of sight and produces a pulse profile. The profile has a leading edge and a trailing tail. The leading edge is sharp, the trailing side is softer. Then the profile changes. The leading edge becomes slightly less steep. The peak shifts within the profile by a small fraction of its width. The first concept is pulse profile stability. Profile stability is repeating pulse shape over time. The definition stays brief. A stable profile allows a consistent reference point in phase. That reference point is used for timing. The payoff arrives quickly. If the profile drifts, timing can drift even if rotation does not. The second concept is mode changing. Mode changing is switching between two stable emission states. The definition stays short and calm. In one mode the pulse is narrow, in another mode it is wider. The switch can be abrupt, yet each mode can remain stable for long stretches. The payoff is immediate. Recognizing modes allows separate timing templates, reducing false timing noise. The visual anchor slows and becomes specific. The magnetosphere is imagined as a set of curved field lines rising from the polar cap. The polar cap is a small oval region. The oval has a crisp boundary. Above it, the plasma density changes with height. The density forms layers like faint smoke sheets. The emission ring sits within these layers. When the magnetosphere shifts, state the ring's brightness pattern shifts. The ring is the same ring, but its brightest arc slides along the circumference. The pulse peak then arrives slightly earlier or later within the profile. The payoff is gentle. Timing depends on a chosen fiducial point, and that point can move when the beam pattern moves. A single rounded number anchors the scale of how small a shape drift can matter. A shift of about 1% of the pulse width can bias arrival times by about a microsecond in a millisecond pulsar, like misplacing a bookmark by a single page in a thick book and noticing only after many rereads. The comparison keeps the effect soft and familiar. The shift is tiny, yet repeated ticks make the tiny accumulate into a measurable bias. Another visual anchor appears as a slow overlay of pulse shapes. Imagine many pulses stacked in memory, most align perfectly. Then a second family appears. Its peak is slightly offset, its tail is slightly longer. The offset is not random scatter, it is coherent. The payoff arrives. Coherence suggests a state change rather than measurement noise. The narrative moves through a checkpoint about timing practice without describing any human activity. Timing uses a template. A template is a standard pulse shape used for alignment. The definition stays short. When the actual shape differs from the template alignment, error can occur. If modes are present, separate templates are needed. If gradual shape evolution occurs, a single static template may introduce systematic residuals. The payoff is calm. Shape awareness can preserve timing precision by keeping the reference point consistent. The analogy for this section stays singular and quiet. The situation resembles a lighthouse beam seen through slow fog bands. The rotation of the lighthouse is steady, yet the fog changes how the beam edge looks. Sometimes the edge is crisp, sometimes it is softened. Sometimes the brightest part shifts within the beam. The timing of the beam sweep is the same. The perceived peak can shift. In the pulsar case, the rotation is the clock. The magnetosphere is the fog band system. The payoff remains clear. A stable clock can still show apparent jitter if the marker being timed changes shape. Another visual anchor brings attention back to physical structure. The open field line region forms a boundary like a rim. Inside the rim, particles stream outward. Outside field lines close. The boundary can move slightly as conditions change. A small motion of this boundary can change which part of the emission cone is active. The pulse width then changes. The peak can move. The trailing gradient can deepen or flatten. The payoff arrives gently. Small geometric shifts in the emission zone can translate into phase shifts. The limit of observation enters with clear boundaries. The magnetosphere cannot be mapped directly. Only the pulse shape and timing are available. Different magnetosphere configurations can produce similar profiles. This is a limit of inference. A stable profile does not guarantee a unique geometry. Another limit is cadence. If modes switch faster than the averaging time used to measure the profile, the measured shape becomes a blend. The blend can hide the true modes and introduce extra noise. This is a limit of measurement resolution in time. The payoff stays practical. Longer, cleaner sequences allow separation of modes. Shorter sequences can blur them into apparent jitter. The story moves through another checkpoint about long baselines. Over years, some pulsars show gradual profile evolution. The evolution can be slow. It can be linked to a slow change in orientation or plasma distribution. The pulse peak can drift slightly. If not tracked, the drift can mimic a change in spin frequency. The payoff is calm. Distinguishing shape drift from spin drift protects the clock interpretation. The visual anchor slows again. The emission ring is imagined as a thin, glowing bracelet around the magnetic pole. The bracelet has a brighter bead that slowly slides along it. The bead is not a separate object, it is the region of stronger emission. As the bead slides, the pulse peak slides. The rotation stays constant. The bead motion changes the marker. The physical detail remains the bracelet's ring shape and the bead-like brightness gradient. The scale shift widens gently. A microsecond bias arises from a tiny shift within a pulse profile. That tiny shift can matter when pulses are counted across years. The same record that reveals orbital decay and interstellar dispersion also reveals emission state changes. The clock is therefore a layered instrument. It measures rotation. It also exposes the behavior of the magnetosphere. The closing transition stays soft, with pulse shape stability, and magnetosphere modes now part of the timing story. The next section can widen to the rarest sources. It can show why certain millisecond pulsars become the quietest long-term clocks and what makes them so steady over decades. Some pulsars behave like clocks that never quite settle, while a small subset repeats with an almost unnerving calm. The most stable long-term clocks are usually recycled millisecond pulsars with smooth spin-down and steady pulse shapes. In that region, stability is built from three quiet conditions. Rotation is fast and regular. The breaking torque changes slowly. The beam pattern stays similar across many years. The scene opens on a compact star that is not shown as a surface of detail. It is shown as a dark sphere with two faint polar ovals. Each oval has a thin, bright rim. The rim is a physical boundary. It is sharper on one side and softer on the other. A narrow cone of emission extends outward from each oval. The cone edge looks like a clean geometric line. It sweeps across space with each rotation. The first concept is recycling. Recycling is spin up by long-term mass transfer in a binary. The definition stays short and the mechanism stays visual. Material forms a disk around the pulsar. The disk is not a solid object. It is a thin, rotating sheet with a denser inner ring. The inner ring rubs and heats. It also carries angular momentum inward. Over long spans, the angular momentum nudges the star into a much faster rotation. The payoff arrives early. A recycled pulsar gains a short period and has a smoother external environment, and both effects support clock-like timing. A single rounded number anchors the idea of fast ticking. A typical recycled pulsar can spin once in about 2 milliseconds, like a beacon that flashes about 500 times each second. The comparison keeps the scale immediate. 2 milliseconds is too small to picture as a duration. 500 flashes each second gives the mind a rhythm. At this distance, fast ticking does not only look impressive, it also creates redundancy. Many ticks arrive in a short span. Random jitter that shifts one tick can be averaged across many. The clock does not need each tick to be perfect, it needs the long-run count to be consistent. The visual anchor slows again, the beam edge passes across an imagined reference line in space. Each pass creates a sharp leading edge. The leading edge is a consistent marker. The trailing side fades with a gentle gradient. The payoff is clear. A sharp edge provides a stable phase reference that resists small shape variations. The second concept is spin-down torque. Spin-down torque is the braking that slows rotation over time. The definition stays brief and calm. Torque comes from electromagnetic forces in the magnetosphere. A stronger magnetic field tends to produce stronger braking. A weaker field tends to brake more gently. In many recycled pulsars, braking is gentle and smooth. The pulse period still lengthens. It lengthens very slowly. The payoff arrives quietly. A smooth brake makes timing models simpler because long-term trends are easier to remove without leaving structured residuals. The physical detail returns to the magnetosphere. Field lines rise from the polar region. They curve outward. They create a funnel of open lines where particles stream away. The boundary between open and closed regions is a rim. The rim can shift. When the rim holds steady, the emission cone holds steady. When the rim jitters, the cone edge can wander. The payoff lands. Beam geometry stability matters as much as rotation stability. A stable beam keeps the timing marker fixed. A stable brake keeps the rotation phase predictable. The analogy for this section stays singular and natural. The stable millisecond pulsar resembles a deep ocean tide under a calm surface. Small ripples ride on top. The tide remains steady and predictable. The ripples are short-term noise. The tide is the long-term phase evolution. The payoff is immediate. Timing models track the tide and treat the ripples as scatter. Faster rotation increases the number of samples of that tide. The narrative moves through a checkpoint about what makes some pulsars noisy. Young pulsars can glitch. Glitches are sudden increases in rotation rate. The definition stays short. Glitches often involve internal superfluid coupling. The coupling can release stored angular momentum into the crust. That release produces a sharp step in phase. The payoff is clear. A single glitch can ruin a simple long baseline model. Recycled millisecond pulsars glitch far less often. Their rotation is usually more placid. Their magnetospheres also tend to be less variable on long timescales. The visual anchor shifts to an interior image without claiming direct sight. Inside the star, a superfluid region is imagined as a layered core. The layers are smooth. The boundary between layers can pin vortices. Vortices are tiny rotation threads in superfluid. The definition stays short. When many vortices unpin together, a glitch can occur. This is a limit of intuition. The interior cannot be observed directly. The layers and vortices are inferred. The payoff remains gentle. Even without direct access, the timing record reveals whether the interior behaves smoothly or episodically. Another checkpoint arrives about propagation. Even a perfect pulsar clock sends pulses through an imperfect medium. Interstellar electrons cause frequency-dependent delays. Those delays drift as the line of sight samples different plasma structures. The physical detail is the scattering tail that can smear a pulse. The tail is a faint extension that follows the main peak. The tail length can change as scattering strengthens or weakens. The payoff is clear: stable clocks still need stable propagation corrections to preserve their best precision. The limit of observation becomes specific. The electron distribution along the path cannot be mapped uniquely from timing alone. Different plasma screens can produce similar delays. This is a limit of modelling. Long-term drifts can mimic low-frequency timing noise. The remedy is not perfect. It relies on separating correlated and uncorrelated effects across many pulsars. Another limit arises from pulse shape evolution. Even in recycled pulsars, subtle mode changes can occur. If the leading edge shifts, arrival time estimates can shift. That shift can look like a spin irregularity. The payoff remains calm. The most valuable clocks are those whose beam edges and polarization structure remain steady for decades. The visual anchor slows into a long baseline view. A pulse train stretches across years like a faint ribbon. On the ribbon, each pulse is a notch. The notches are nearly evenly spaced. The ribbon is not perfectly straight. It curves gently due to spin down. It also has tiny waviness due to propagation and profile noise. The payoff arrives. A stable millisecond pulsar is the case where the ribbon curvature is smooth and the waviness is low. The scale shift widens softly. 2 milliseconds sets the tick scale. Years set the baseline scale. The same object bridges these extremes by repeating an enormous number of rotations with small cumulative error. That is the quiet reason pulsars can rival atomic clocks in long-term stability. It is not magic. It is repetition plus smooth physics plus careful separation of effects. The closing transition stays gentle. With the reasons for extreme stability now laid out, the final section can step back from mechanisms. It can hold the idea of timekeeping as a calm landscape and let the pulse rhythm fade into a softer perspective. A pulse train can sound like a simple metronome. It is also a map of space-time written in small delays and steady returns. In that region, the deepest lesson is quiet. Timekeeping in the cosmos is not a single perfect clock. It is a layered agreement between rotation propagation and modelling. The scene opens with a wide dark field. Points of light appear and fade in patient rhythm. Each point is not a star in detail. It is a timing mark. A faint imaginary grid lies across the field. The grid is made of soft lines that meet at right angles. The lines are not rigid. They breathe. The physical detail is the subtle change in spacing between grid lines, a gentle stretch in one direction and a gentle squeeze in another. The first concept is phase. Phase is position within a repeating cycle. The definition stays brief. A pulse arrival marks a phase. Many arrivals create a history of phase. That history becomes a ruler for time. The payoff arrives early. Counting phase is the core of pulsar timekeeping. It turns a spinning object into a long baseline clock. A visual anchor slows and becomes simple. Imagine a long ribbon laid across darkness. Along the ribbon, evenly spaced notches appear. Each notch is a pulse. The spacing is almost uniform. Over long spans, the ribbon curves slightly. The curve is spin down. The notches also show tiny irregularities. The irregularities are propagation and profile effects. The payoff remains calm. The clock is seen as a pattern with a smooth trend and small departures. The second concept is timing residuals. Timing residuals are differences between observed and predicted arrivals. The definition stays short. Residuals are where the universe hides its extra information. If a model captures rotation and known delays, residuals can reveal a new effect. If the model misses a beam shift or plasma drift, residuals can also mislead. The payoff is immediate. Residuals are both signal and suspicion. They require careful separation of causes. A single rounded number anchors the ending scale shift. A millisecond pulsar rotates about 500 times each second, like a calm drum beat that repeats hundreds of steps before a single breath feels complete. The comparison keeps the rhythm gentle. The scale shift widens. Hundreds per second becomes millions per hour. Hours become years. Years become decades. The same repeating notch becomes a bridge between the smallest accessible time slices and the largest patient baselines. The visual anchor changes to a quieter geometry. A circle is imagined around a polar region. The circle is the emission ring. It has a thin, bright rim and a softer interior. The rim is not perfectly uniform. One arc is brighter. One arc is dimmer. The arc is a gradient. As rotation proceeds, the arc sweeps past the line of sight and sets the pulse shape. The payoff arrives. A stable rim and gradient create a stable marker. When the gradient drifts, the marker drifts. That is how magnetospheres enter timekeeping without ever being touched. Another checkpoint returns to propagation. The line of sight is imagined as a long corridor through a thin mist. The mist is not uniform, it has sheets and pockets. The sheets create dispersion and scattering. The scattering adds a faint tail to each pulse. The tail is a physical detail. It stretches behind the main peak like a soft smear. When the corridor changes, the tail length changes. The payoff is calm. Even a stable clock can look less stable when the corridor changes. Another checkpoint returns to arrays. Many ribbons are laid together. Each ribbon is a pulsar residual series. Most wander in their own way. Then a faint coordinated bend appears across many. The bend depends on sky separation. It is not identical everywhere. It is patterned. The payoff lands softly. A shared spacetime effect can be found by agreement among many independent clocks. That agreement is the strength of the method. The analogy for this final section stays singular and gentle. The ensemble of pulsars is like a grove of wind chimes spread across a wide valley. Each chime rings with its own tone and small local flicker. A slow breeze passes through the whole valley and changes many chimes at once in a related way. The breeze is not seen, it is inferred from the shared shift in timing. The payoff is simple. A large pattern is recognized by comparing many small patterns. The limit of observation is stated with clear boundaries. The interior of a neutron star cannot be observed directly. The magnetosphere cannot be mapped uniquely. The interstellar plasma cannot be fully reconstructed from a single line. Even space-time ripples are not seen as waves. They are inferred from timing correlations. This is a limit of inference. It is also a limit of resolution. Very slow changes can mimic each other. Very small changes can hide within noise. The payoff stays gentle. The method remains powerful because it relies on repetition and cross-checking rather than direct images. The closing visual anchor steadies and softens. The grid lines across the dark field continue their faint breathing. The notched ribbons continue their slow procession. The emission rings continue their steady sweep. The whole system feels like layered rhythms. Rotation provides the bass beat. Propagation adds a soft filter. Modelling removes known structure. Residuals hold what remains. The final payoff arrives without sharpness. Pulsars keep time well because a simple physical cycle repeats with extreme regularity, and because differences can be averaged and compared across long spans. The ending transition becomes a landing rather than a doorway. The field of pulsing points grows quieter in imagination. The notches on the ribbon become less distinct. The sense of counting gives way to a sense of steady presence. In that calm, the idea of cosmic timekeeping remains as a soft background rhythm that does not demand attention.